Hindi.
Hindi. Anything else? Or we?
Sanskrit.
Sanskrit? No.
We will not understand. He will speak. Very right. G.
Okay, we may start.
Yeah. Ma'am is live streaming on YouTube. Once that is done, we will immediately start.
बोलतात आहे नुसते एकमेकांशी.
Sir, please start.
Okay.
It's
So,
started.
welcome to all those who have joined online today. Today is the final and third day of our Curtain Raiser program. And we have once again today one eminent speaker, Professor Vijay Podbare from MS University, Baroda. So without wasting any time, I would request Professor Dheeraj Shah, who is a faculty member in Sir P.T. Saravajanik College of Science, to give introduction of today's speaker, Professor Podbare. Dheeraj, it's up to you.
Yeah, thank you, sir. Good evening, one and all present over here. It gives me immense pleasure to introduce our today's speaker, Dr. Vijay Podbare, sir. Vijay Podbare, sir, did his BSc in 1967 and MSc in 1969 in the physics subject from MS University, Baroda. Then he joined Theoretical Nuclear Physics Department at University of Rochester and completed his PhD in Theoretical Nuclear Physics. Then he did his PDF at University of Toronto from 1975-76. And after that, he joined as a research scientist at Physical Research Laboratory from the year 1976 to 78. After that, he joined as a lecturer at South Gujrat University in the year 1978. And then after that, he joined MS University, Baroda. From 1978 to 86, he was there as a reader. And then from 1986 to 2009, he worked as a professor of applied physics at MS University, Baroda. Apart from that, as I'm teaching in physics department at Sir P.T. Saravajanik College of Science, Surat, we have one very good program where 3 days program we had in past, and we know the Podbare sir very well, and the kind of lecture he has delivered at our place, we still remember. So I'm quite happy to introduce him. Thank you, sir. Over to you, sir. Pruthul, sir.
Yes, sir. Podbare, sir. Thank you, Dheeraj. And the stage is yours, sir, now.
Okay, can I share the screen?
Yes.
Pruthul, if you can, at a later date, share all the YouTube links.
I'll do that, sir.
Thank you.
Good evening and Jai Shri Ram to everyone.
Namaskar. Jai Shri
Namaskar.
Namaskar. Namaskar. Today's topic, of course, is uncertainty principle. And uncertainty principle is something which is very important in quantum mechanics. Without it, of course, quantum mechanics will not stand. Anyway, uncertainty is very important in our life also, because without uncertainty, there is no happiness, there is no grief, there is no joy. Otherwise, everything will be boring and routine. So uncertainty is very essential in our life also, because without uncertainty, what is going to happen next? If something that is, if everyone knows about it, then of course there is no reason, because everything is going to happen according to the law. But uncertainty principle is a principle, of course, in everyday life also, but uncertainty in physics, that is very important. As far as the
sorry, Podbare sir, can you make your full screen? F5 or what?
F5, sir.
Yes, sir.
At
Press
the
F5 so
bottom
it will.
taskbar, there will be.
हाँ
F5 press કરો ને તો પછી slide show માં જાઓ અને ત્યાંથી you can do it. Yeah,
अभी क्या
done.
okay
Perfect.
okay. As far as the uncertainty, I mean, as far as the science is concerned, there are many important events in science. For example, Darwin's Origin of Species, synthesis of urea in laboratory, understanding genetic code by Crick and Watson, Fleming's discovery of penicillin, invention of number system, which is very important in science. Similarly, Gödel's impossibility theorem, cloning and genetic engineering, Wegener's theory of continental drift, Euclid's postulates, and geometry. Of course, the list can go on and on and on. Particularly in physics, there are very important things that like Newton's theory of gravitation, Ørsted's experiment, Maxwell's equations, Einstein's theory of relativity, quantum mechanics, thermodynamics and arrow of time, nuclear energy, lasers, semiconductors, and then there is a talk by Feynman, which basically talks about nanotechnology and so on. Now, of course, one can add, can you listen properly, hear properly?
Yes, sir. Yes,
okay. So, I don't know how to remove this particular thing from the bottom.
You take it to the left.
Okay. Okay. So that
So back arrow key once.
okay. So therefore, artificial intelligence and each of these has changed our thinking and revolution of a kind. Now, all these things are connected together. Everything in our life, everything in this world is connected together. Whatever happens here is connected to everything in the universe. For example, there is a poem written by John Donne, which says, "No man is an island, entire of itself. Every man is a piece of the continent, a part of the main. Any man's death diminishes me because I am involved in mankind, and therefore never sent to know for whom the bell tolls. It tolls for thee." Tolling of a bell in Christian mythology basically means that somebody in the village, somebody in the town has died, and please come to the church. That was so therefore, in principle, everyone is connected to each other. And as far as that part is concerned, the uncertainty principle is also connected to everything in the universe. The quantum revolution started beginning of the last century with Planck's hypothesis in 1900. This started at the beginning of last century, and still it is not completely understood. Feynman, once upon a time, he said, there was a time when the newspaper said that only 12 men understood the theory of relativity. He says, I do not believe that there ever was such a time. On the other hand, I think I can safely say that nobody understands quantum mechanics. Nobody knows how it can be like that. Quantum mechanics is something which is very hard to understand, and that is, of course, that quotation is from Feynman's book, Character of Physical Law. Then Professor Bohr also commented, those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. So, and then it is Professor Einstein also has said that Professor Einstein basically says that, can you see the slide completely?
Yes, we can. Yes.
Yes, we can.
Yes, sir.
Professor Einstein said, all these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick and Harry thinks he knows it, but he is mistaken. Anyway, these are some of the comments by the giants who have made quantum mechanics And they basically say that it is very hard to understand. So where is a person like me who's trying to explain uncertainty principle? Anyway, the main concept which gives us the Heisenberg uncertainty principle is the concept of duality, wave-particle duality. As far as light is concerned, interference and Young's double-slit experiment basically tells that light is a wave, while photoelectric effect and other like Compton effect, etc., basically tell that light is a particle. Similarly, matter, as far as the electrons, protons, neutrons, and all other particles, and every particle that is there in the universe, electrons are particles was proved by J.J. Thomson, while it is a wave was proved by his son, Thomson's experiment, and also by Davison-Germer experiment. Whenever we describe anything like a wave, then as far as the description of a wave is concerned, uncertainty in position is infinity, because wave extends from one end to the other end. At that same time, if you describe it as a wave, the momentum uncertainty is zero, because it has definite wave vector, definite k, and therefore definite momentum. When we describe it as a particle, then particle is at a particular position, and since it is at particular position, delta x, that is uncertainty in position, is zero. At the same time, it can be described as a superposition of infinite amount of waves, and therefore delta px, that is uncertainty in momentum, is infinity. Now, as far as the wave packet is concerned, therefore one has to introduce what is a wave packet. The wave packet is basically a superposition of many waves, and it is partly localized. It is because there are many waves superposed to each other, and that is given as psi xt as an integral of ak. Ak is the amplitude of wave k multiplied by e to the power I kx minus omega t. That is basically a wave. Now, Fourier theorem is there in mathematics, which basically says delta x, delta k is greater than 1 over 2, because as far as the wave description and particle description are converted to each other by Fourier transform. Now, as far as the definition of uncertainty in x and uncertainty px is, this is a standard definition, and that standard definition basically says delta x is the square root of expectation value of x squared minus the expectation value of x squared. Similarly, for delta px. Now, as far as this is concerned, uncertainty basically means we talking about wave packet, wave, and wave, as far as our quantum mechanics is concerned, talks about probability, because psi star psi corresponds to probability. Now, probability enters in physics via quantum mechanics, while it already had entered earlier in statistical mechanics. In statistical mechanics, the probability entered not because of any reason, but basically because our inability to collect entire data of all matter. But in quantum mechanics, probability is intrinsic in character, while in statistical mechanics, it is because there are so many number of particles that we cannot collect the data for all the particles. Now, as far as quantum mechanics is concerned, whenever we talk about quantum mechanics, non-locality also comes into picture. Anyway, we are not going to talk about derivation of uncertainty principle, because derivation is given in most of the textbooks. Our purpose, my purpose of here is to use or try to understand what are the things that we can understand using uncertainty principle. I'm going to discuss following topic, but before discussing the ideas involved applied to various aspects, I would like to remind you of a very important remark by Professor Feynman in his lectures on physics. He says in lectures on physics, the uncertainty principle protects quantum mechanics. Heisenberg recognized that if it were possible to measure the momentum and the position simultaneously with a greater accuracy, the quantum mechanics would collapse. So he proposed that it must be impossible. Then people sat down and tried to figure out ways of doing it, including Einstein. And nobody could figure out a way to measure the position and momentum of anything, a screen, an electron, a billiard ball, or anything with any greater accuracy. quantum mechanics maintains its perilous but still correct existence. Now here I'm going to talk about many things. As far as first thing that I will talk about is gamma ray microscope, then Einstein's suggestion for using diffraction, and then Einstein's box, then double slit experiment, and there are many applications. Applications include electrons, whether electrons are there in nuclei, protons are in the nuclei, stability of hydrogen atom or matter, origin of repulsive interaction, rejection of semi-classical picture of Bohr orbits, resonance energy, hydrogen molecular ion, natural line width, inability to solidify helium, ground state energy estimation of hydrogen atom, harmonic oscillator, statistical mechanics and elementary phase space volume, vacuum polarization and its role in spontaneous emission, barrier penetration, smallest uncertainty product for Gaussian wave packet, ground state harmonic oscillator, range of nuclear interaction, coherence length and in superconductivity, and then its role in philosophy, smallness of effects in classical region, smallest uncertainty product for Gaussian wave packet, resonances, large molecules, vacuum polarization, and charge of the electron, and Hawking radiation, Maxwell's demon, and arrow of time. Now let us first begin with gamma ray microscope. If I want to look at an electron, if I want to size of an electron, I must have a wave which is smaller than the size of an electron. Wavelength of is something where the object is to be observed. The light is allowed to light is allowed to fall on it, and then basically it is scattered in the microscope and it enters the microscope lens, where when it enters the lens, it half angle of the aperture of the microscope is theta, so therefore delta x, which corresponds to wavelength divided by 2 sine theta. Now electron is certainly smaller than the visible photon, must use small wavelength, and ultimately when we use the small wavelength, hence the gamma ray photon. So initial x momentum photon is p, x component of photon after scattering. When the photon is scattered into the lens, we don't know from where it enters, so therefore it basically enters in the cone, and therefore uncertainty corresponds to p sine theta, and therefore if you take delta x into delta px, it basically turns out to be lambda by 2 sine theta multiplied by p sine theta, which corresponds to h by 2. So the process of measurement affects that which is measured. Now the electron is no longer stationary there. Of course, the electron was not stationary anyway, but the electron basically now has moved to some other place. Now, as far as the diffraction is concerned, the diffraction is also a phenomena corresponds to matter. And as far as the first minimum is concerned, the first minimum corresponds to at theta at lambda by a. And therefore, uncertainty in the x momentum is given by the angular spread, which is again p sine theta. So reduction in the position uncertainty increases the uncertainty in the momentum. So basically delta px corresponds to h upon delta x. So reduction in position leads to increase in momentum uncertainty. Einstein says that if the momentum of the photon is measured indirectly as it leaves the slit, we can make the uncertainty product as small as possible. This can be done by measuring the momentum transferred to the slit. But the slit is connected rigidly to the earth, and therefore it's not possible to measure its recoil. And therefore, one has to use the shutter to open the slit for delta t. That is what Einstein said. Measure energy transfer to the shutter, and then the momentum can be known. Anyway, that is something which we will come across. Here is a experiment which is not necessarily for the diffraction is not necessary for electron, neutron, or proton. Here is a particle which corresponds to carbon 60. that is basically buckyball. If you take a buckyball, it also with a certain velocity, the experiment has been done with buckyball, which shows that it also has a diffraction pattern. This is another C60 experiment using different velocity, and therefore this is also a diffraction pattern. Now, as far as the diffraction pattern is concerned, speed of the shutter, that is basically what Einstein's argument says, that if I measure the speed, energy transferred to the shutter, then the speed of the shutter corresponds to delta x by delta t, and energy corresponds to V half mv square. Change of energy corresponds to delta half mv square. And if we take that uncertainty, then delta E into delta T comes out to be of the order of h bar, which corresponds to delta x into delta P. Einstein, in early days, in the 1920s, 1926, 27, there used to be many conferences. One of the famous conferences corresponds to Solvay conferences, where Professor Einstein and Professor Bohr could meet each other, and they used to discuss. Bohr, initially Einstein was very instrumental in bringing the quantum mechanics in, but as far as the uncertainty principle is concerned, Einstein did not like the probability interpretation of Copenhagen, and he used to oppose Professor Bohr by giving various examples, and they're saying that if you do this, then the uncertainty product will be smaller than h. He is one of the examples that Professor Einstein gave, that supposing you have a box full of radiation. This is a box that is full of radiation, and there is a shutter, and shutter is controlled by a clock. So when the shutter is open, the energy will move out. Now energy will move out at that particular time. You know what is the time, and then the energy moves out means the mass of that particular thing will reduce, and therefore the weight will be changed. So the measure the energy escaped of radiation by weighing the box, and knowing when the shutter is open, you know what time it is. So therefore, in principle, you can both measure the energy and time at a distant detector. You can predict. Hence the violation of energy and time uncertainty product. Now, this is what used to happen. So Einstein would give problem to Professor Bohr during the lunchtime, and then lunchtime or breakfast, and then Bohr could not sleep the entire night, and the next day he would answer the question. Now, as far as this particular thing is concerned, Bohr answered the question very easily. I'm not going through the mathematics part of that, but basically says that this particular experiment or this particular thought experiment can be solved by using Einstein's general theory of relativity, because general theory of relativity says that if the position is changed, then the gravitational energy changes, and as soon as the gravitational energy changes, the rate of clock changes, and therefore there is time uncertainty involved, and there is energy uncertainty involved, and therefore delta T and delta E always greater than h bar. Anyway, that is besides the point. So as far as this is concerned, the uncertain, as far as the double slit experiment is concerned, this is one of the most important. The experiment nearly underlines the basic feature of quantum theory. That is what Feynman basically says, that this is the basic understanding of quantum theory. We know very well that because of the uncertainty and because of the quantum nature of the particle, we get interference pattern. Now, each photon, as far as the photon is concerned, each photon interferes with itself. This is, and Bohr, who says that those who have not shocked when they come across quantum theory possibly could not have understood it. So this is another experiment which basically shows that interference effect occurs also for large particles. This is the image of interference of phthalocyanine molecule. Each dot is a single molecule detected by fluorescence, and the pattern of the strips is indicative of wave behavior. Anyway, let us come to the next part. As far as the electrons are concerned, electrons are not in the nucleus. That of course is very clear. Electrons move around the nucleus, and if the electron happens to be in the nucleus, the radius of the nucleus is very small, that is of the order of 10 to the power minus 13 centimeter. Then you can calculate what is going to be delta P. Delta P is going to be h upon r0. And if you consider that momentum is very large, and therefore electron momentum would be of the order of 200 MeV. And when the beta decay occurs, you never see a beta decay which is roughly more than 2 MeV particle or 3 MeV electron coming out. And therefore 200 MeV electron never comes out. So that basically means that electrons do not have, even for uranium nucleus with Z is equal to 92, potential energy is of the order of 125. Electron comes out with energy of 200 minus 175 MeV. No beta decay with such large energy. And that basically means electrons do not exist in the nucleus. Electrons are created whenever beta decay occurs. While the proton can exist inside the nucleus, because proton has a mass much larger than the electron. Proton has a mass 200 times more than the 2000 times more than the electron, and therefore we require no relativistic treatment, and kinetic energy corresponds to of the order of 20 MeV, and potential well must be deeper than 20 MeV. So usually the potential well of the nucleus potential is much deeper than that, and therefore proton has requirement of stability. What is requirement for stability? Stability requirement basically says that as far as the stability is concerned, we must have attraction for a long range and repulsion for short range. Now for each atom, potential energy is of the order of minus 1 over r, and kinetic energy is of the order of 1 over r squared due to uncertainty principle. Right? Because if it is kinetic energy is of the order of 1 over r square, because delta x, uncertainty in position is of the order of r, and momentum is divided by h over r. So kinetic energy is square of the momentum. So same thing for hydrogen atom, attraction due to Coulomb interaction and repulsion due to uncertainty principle. Same thing happens for ionic bond in sodium chloride. In sodium ion and chlorine ion, both have spherical charge distribution. And if we have spherical charge distribution, we can treat them as point particles. But as far as the point particles are concerned, they are attracted by Coulomb interaction, while the repulsive interaction is due to overlapping of electron orbits. Electron orbits overlap each other, and therefore they are confined to a smaller and smaller space. And since they confine to smaller and smaller space, they will have to have larger kinetic energy, which basically means they cannot come together because the energy cannot be produced. Repulsive interactions due to overlapping uncertainty increases momentum uncertainty, requiring increase of energy cause for the repulsion. For example, stability of matter, and stability of matter is precisely because of the uncertainty principle. Now, quantum mechanics, even though we began quantum mechanics with quantum, the idea of quantum came with Planck, and Einstein gave photoelectric effect and so on and so forth. But as far as the 1913, Bohr gave the picture of hydrogen, that hydrogen electron orbits are going around, and then that is basically started the entire game. Now, as far as the electron picture is concerned, we cannot actually use semi-classical Bohr picture. Now, Bohr picture basically says that electrons going around. So allowed orbits in the Bohr orbit says PR, that is MVR, corresponds to n times h bar. In order to talk about orbits, we must have delta r, that is uncertainty or change of radius is much smaller than r. That basically means delta p must be smaller than p. So delta r by r and delta p by p must be smaller than, much smaller than 1. Then and then only we can talk about orbits. if everything is going round and round or going from one place to another place, fluctuating, then we cannot define an orbit. So, however, uncertainty relation requires delta R delta P must be larger than H. So, delta R delta P divided by Rp corresponds to H upon 1 upon N. So, therefore, these two relations are incompatible because if N is much larger than 1, they are compatible only if N is much larger than 1, because otherwise uncertainty relations makes us reject the concept of orbit. For large N, however, we are back to the classical regime. Then it is all right to talk about orbits. This is Bohr's correspondence principle. Bohr's model is merely a way to obtain correct energy spectrum for the hydrogen atom. And we know very well now that electron behaves like a cloud around a nucleus. Now, this is one very nice application of uncertainty principle, which comes from chemistry. As far as the benzene molecule is concerned, famous Kekulé is famous for that. Kekulé was trying to understand the benzene molecule, and we know the story of Kekulé, that Kekulé dreamed about the benzene structure, that Kekulé dreamed that a serpent is eating his own tail, and so therefore this is how Kekulé gave a structure of benzene as such, that benzene corresponds to 3 double bonds and 3 single bonds with 6 carbon atoms connected to each other by 3 double bonds and 3 single bonds. But now, which 3 double bonds and which 3 double bonds? Number 1 and number 2 both have 3 double bonds and 3 single bonds. So therefore, whether this or that, now in principle, it turns out that both these structures are possible, and that basically means electrons can really go around. Double bond basically means single bond basically means 2 electrons are restricted to a certain region. Double bond corresponds to 4 electrons restricted to a region, while in benzene every bond is, so therefore electrons are not really restricted to double bond, they actually go around and round and round, and therefore uncertainty in the position of the electron is increased. And because of the uncertainty in electron position is increased, momentum uncertainty is decreased. And since the momentum uncertainty decreases, the energy decreases, and that gives extra stability to benzene molecule. Typically, as far as the chemists are very clever fellows, they know what is the distance between the carbon atoms for the single bond and double bond. As far as the double bond, single bond length is concerned, normally it is 1.54 angstrom, and double bond length is 34 angstrom. While in benzene, it is neither single bond nor double bond. It is 1.40 angstrom, 1.40 angstrom, which basically means every bond is more or less the same. So as a consequence of electron delocalization, that is, the electron is delocalized, and therefore it gives extra binding energy to the benzene. The extra binding energy corresponds to 1.6 electron volt per molecule. And for naphthalene, naphthalene is double, 2 rings together, and that basically gives you 3.26 electron volt per molecule. Now, another very important consequence of uncertainty principle is our protein structure. Protein structure basically corresponds to a peptide bond. Peptide bond corresponds to C double bond O and N. Carbon is connected, C double bond O, and connected to N. Now, the actual structure basically corresponds to not a single bond around N, it's oscillating bond. That is, the double bond between carbon and oxygen comes out to be double bond between carbon and nitrogen, and the electron oscillates from this place to that place. So therefore, this is basically oscillation because of the carbon and nitrogen bond has considerable double bond character. Now, this double bond character has 2 consequences. One consequence is, of course, is the extra binding energy that corresponds to extra 1 electron volt energy for the peptide bond. And the second consequence is that the molecule cannot rotate around that particular bond, because if a single bond is there, the molecule can rotate around, and that gives a stability, that gives a three-dimensional structure to protein. And without that three-dimensional structure of protein, without that peptide bond, our protein structure would not be stable. So this is very important for biology or biological thing, because our body is mainly made up of proteins. Now this is another place where you talk about hydrogen molecular ion. Hydrogen molecule ion. So hydrogen molecular ion means 2 protons and 1 single electron. All right. When protons are far apart, electron will stay with 1 proton, and so therefore if there are 2 atoms, then the state number 1 corresponds to electron around proton number 1 and proton number 2 without an electron, while state number 2 corresponds to proton number 1 and electron around the proton number 2. So these are 2 states. This is electron around proton number 1, no electron around second proton. This is second state, which corresponds to no electron around proton and another electron around proton number 2. Now, actual state is the superposition of these 2 base states. These are 2 base states. This example comes from Feynman's Feynman lectures, volume number 3, where he talks about hydrogen molecular ion. Now, in principle, there were the 2 possible structures are there. That is, one possible structure is that the 2 states are state 1 and state 2 with a minus sign in between, and 1 over root 2 is basically because both are identical, and therefore 1 over root 2 basically is an amplitude of each state. The second state corresponds to addition of these 2 things. Now you can immediately see that in state number 2, electron can also exist between the 2 plates, because they are so therefore it is compared to state 1, state 2 has more spread out electron wave function. Since it is more spread out, the delta x is larger, and therefore delta px is lower, hence lower energy than state number 1. If we take into account the distance between the protons and proton repulsion energy, probability of electron to jump from one proton to another proton, the detailed analysis gives the energy as in next figure. Next figure basically tells me that energy of the molecule, where with distance between the 2 protons on the x-axis and the energy. So energy of state 1 always goes on increasing, while energy of state 2 has a minimum. Therefore, hydrogen molecular ion is a stable structure, because for stability we require attraction at large distance and repulsion at the lower distance. Now in state number 1, which corresponds to this particular, there is no attraction at all. So here there is attraction and there is repulsion. So the energy levels of H2 plus ion corresponds to that particular thing. Similarly for hydrogen molecule also, we have 2 protons and 2 electrons. Now both electrons can have same spin. Both electrons could have different spin. If they have same spin, of course, you cannot exchange the electron. So actual state of superposition of these 2 states again corresponds to state number 2 displays a minimum again due to increased spread of the wave function. So the 1 and 2, and therefore you can immediately see hydrogen molecule is also a stable, and that is basically what is the covalent bond. Now, as far as the lifetime of an excited state is concerned, you know very well that Professor Bohr, when he talked about orbits, he talked about stationary states. Of course, you know very well there is no only stationary state is the ground state. But uncertainty principle relates lifetime of an excited state due to spontaneous radiative decay. Whenever spontaneous radiation occurs with uncertainty of its energy, a short lifetime will have large energy uncertainty and a broad emission, and broadening effect results in unshifted Lorentzian profile. Natural line width of atomic transition. So that basically says if lifetime is small, then the line width is larger, and if the lifetime is very large, then the bandwidth is very small. Now, as far as the laser is concerned, laser has a coherence time, and coherence time is for ordinary gas laser, it is 10 to the power minus 3 seconds. For solid state laser, it is 10 to the power minus 6 seconds, and it is For ordinary light source, it is 10 to the power minus 12 seconds. And we know very well energy uncertainty principle, energy time uncertainty, which basically says delta E corresponds to H upon delta T. So delta nu corresponds to this particular quantity. For solid state laser, the uncertainty in frequency corresponds to 10 to the power 5 hertz, while uncertainty for ordinary light is 10 to the power 17 hertz. So therefore, you can immediately see ordinary light is really broad and very sharp monochromaticity basically means of the order of monochromaticity. Sharpness is even better for gas laser as it is coherence time is much larger than the solid state laser. For ordinary light, however, the natural line width is much larger comparatively. Now, this is another example, basically is using uncertainty principle. Uncertainty principle basically says or can be used to understand why helium cannot be liquefied. Why helium, that I'm talking about helium-4. Helium-4 cannot be liquefied because as far as the helium-4 is concerned, you can immediately see that for helium-4, the potential energy or interaction is only van der Waals interaction. It's van der Waals interaction that is basically giving, this is the potential energy for van der Waals interaction. And we know very well that as far as the energy is concerned, we can talk about energy in terms of temperature. K times T corresponds to energy. So therefore, here the scale on the left hand side basically corresponds to temperature. So the minimum of van der Waals potential for hydrogen helium molecule, right? This is calculated long time ago. So therefore, this basically says that as far as it's the minimum corresponds to roughly of the order of 9K. So therefore, this is of the order of depth of potential well. So therefore, delta X for well-defined location as in solid, delta X should be smaller than the range of the potential. Delta X should be smaller than the range of the potential. The range of the potential is very small. So therefore, delta E must be of the order of 1 upon 2 upon H upon delta X square. So if I take delta X to be 0.5 angstrom, because if I want to make a solid, then the distance between the two atoms should not change by more than 0.5 angstrom. And that basically tells me that delta E, that is uncertainty in the energy, corresponds to 10K. That is roughly of the order. Now the potential well itself only, the well has only 9K as the depth of the potential. And therefore you can immediately say that helium atom cannot be solidified. So you cannot make the helium solid. Of course, you can make helium solid if the pressure is very large, right? And the localization is impossible. Hydrogen H2 solidifies. People ask why helium cannot be solidified, but hydrogen can be solidified, because hydrogen solidifies not only because there is van der Waals interaction. Interaction is no longer van der Waals. It is addition. It has a covalent bond. Other elements do form solids. Other elements do form solids because the mass, because argon is a inert gas, but it can be solidified. Neon can be solidified because the mass is much larger than He, and therefore since the mass is much larger than He, so there is helium is much larger than helium atom. Now, as far as the ground state energy is concerned, you can estimate the ground state energy. You can estimate the ground state energy as for the hydrogen atom. Potential energy is E square by R0, where R0 is extent of spherically, is extent of the sphericity. Kinetic energy is of the order of delta P square upon 2m, H upon 2m R square. So the total energy estimate for the hydrogen atom corresponds to kinetic energy, the potential energy. So therefore, if I minimize this with respect to R0, right, I minimize this, then if I minimize this, then R0 comes out to be H square by me square, and energy comes out to be me square, me raised to 4 by 2H square. Now these two equations give correctly the Bohr atom radius and ground state energy of the hydrogen atom. I mean, don't misunderstand. It is basically accidental perfect agreement. Uncertainty principle does not give you perfect agreement. it only gives you an estimate. So similarly for harmonic oscillator, x0 is uncertainty of the position. So therefore, kinetic energy corresponds to h square upon 2m x0 square plus this is the kinetic energy. This is the potential energy. Potential energy is quadratic in structure. So half m omega square x0 square. Again, we minimize this. Then the ground state energy turns out to be h omega by 2. Again, this also is an accidental number. Now, what about quantum mechanics? Quantum mechanics and statistical mechanics. In statistical mechanics, we know very well that the entropy is given by phase space volume. A number of phase space. In classical statistical mechanics, elementary phase space volume can have any state. Now, this is, you know very well, the formula given by Boltzmann that entropy is k times log of n, where n is the number of states. The number of states corresponds to phase space volume divided by basic phase space cell. Now, phase space cell in statistical mechanics using classical mechanics can have any value. So therefore, entropy in statistical mechanics can have any large value. But in quantum mechanics, it turns out that A cannot be smaller than H. That is, therefore, you immediately come to realize that in quantum mechanics, entropy is restricted. Now, another important understanding using uncertainty principle is the principle of basically spontaneous emission. You know, when we talk about laser, we talk about spontaneous emission and stimulated emission. Stimulated emission depends upon the intensity of radiation, and spontaneous emission is of course spontaneous. And you know very well, Planck's radiation law basically tells me that intensity of radiation of a black body corresponds to this particular formula. This is Planck's radiation law, which began the quantum mechanics in 1900. At equilibrium, now let us consider a system where we have two energy states, energy Em and En. Em is larger than En, and the difference between these two is h omega. That is, omega is the angular frequency, or h nu is the frequency. So at equilibrium, the number of states Nm, that is higher energy states, is smaller than number of states in state N. Now, as far as the emission, now let us consider emission rate. Emission rate corresponds to M to N. So M to N, whenever the system is in higher energy state, it can emit. So the energy state depends on Rmn, corresponding to absorption rate is Rnm. The emission rate consists of two components. Its stimulated emission rate is proportional to number of systems, that is excited state, and also depends upon the energy density. That is stimulated emission. Stimulated absorption also occurs. So it is stimulated emission is written as Bmn times number of particles in M state and multiplied by I omega. That is the density of states, intensity of states in frequency omega. That is I omega. While the spontaneous emission rate is proportional to Nm alone, because there cannot be spontaneous absorption. Right. So therefore, spontaneous emission rate corresponds to two terms. One corresponds to this Amn corresponds to spontaneous emission. Bmn corresponds to stimulated emission. Well, the absorption rate corresponds to only Bnm, Nn times I omega. Because as far as the absorption is concerned, there cannot be spontaneous absorption. Spontaneous absorption means absorption from nothing. So therefore, spontaneous absorption cannot take place because the energy, conservation of energy. So therefore, if you consider these two and then put in the value, so therefore, if you equate these two, that is at equilibrium, spontaneous emission and stimulated emission are equal. If you connect these two together, then you can immediately turn out that as far as the equation is concerned, we obtain the rate of A is the rate of spontaneous emission and B is the rate of stimulated emission. You can, from this, you can immediately see for sun's surface temperature of the order of 6000 K, that is sun's temperature, this lambda is 4000 angstrom. In that particular thing, this basically arouse 30. This indicates that the dominant part of the radiation as we normally experience, except for modern laser source, is dominated by spontaneous emission. Now, if you consider that particular part, putting the values Rmn basically means is the emission rate. Emission rate corresponds to two terms, as far as the number of particles in the higher energy state multiplied by B, and of course there is A by B is known. So therefore, this is what basically corresponds to rate of spontaneous emission. And you can see that this number corresponds to number of particles in number of particles in higher energy state. While this one is something coming out extra. This one extra basically comes in because of the uncertainty principle, which basically says even in the ground state, there is energy of harmonic oscillator which corresponds to h omega by 2. And this is basically called 0 point fluctuation. And this 0 point fluctuation, thus the spontaneous emission is due to virtual photons created temporarily by 0 point fluctuation. These provide necessary perturbation for the emission of photon spontaneously from the excited atom. So therefore, you can immediately see no atom will remain in excited for infinite amount of time, because spontaneous emission will always occur because of the 0 point fluctuation, which comes because of the Heisenberg uncertainty principle. Now, there is another thing that occurs in quantum mechanics, what is called barrier penetration. As far as the barrier penetration is concerned, this is basically what is the barrier corresponds to. And if the object is having energy E, classically, if the object is inside the potential well with energy E, it strikes the potential well and should return back, because classically it cannot go out. But as far as whenever it comes to this particular point, it's uncertain, its velocity turns out to be 0 classically. But you know very well, velocity corresponds to momentum, and momentum has to remain uncertain. So therefore, there is uncertainty in momentum. That basically means there is uncertainty if uncertainty in momentum corresponds to uncertainty in position. So therefore, these are 2 points at which the energy is going to be 0. So if these two, delta x1 and delta x2, that is uncertain in momentum at the first turning point and the second turning point, if delta x that overlap each other, then in that particular case, you immediately see that the particle can come out, or basically barrier penetration can occur. This is because of uncertainty principle. It cannot have both precise position and precise momentum or precise trajectory. So the point at which a quantum particle turns around is not well defined. It is spread over region of delta x centered on classical turning points. And that basically explains why barrier penetration occurs. Now, barrier penetration can also be explained using time uncertainty principle, time energy uncertainty principle. That is because if this is the energy, then in that particular place, as delta E can be, when as far as the uncertainty principle is through time uncertainty. So uncertainty in time also can, so if we, now smallest, now that is how one can understand the barrier penetration. Now, as far as the smallest uncertainty product corresponds to Gaussian wave packet. Gaussian wave packet is the ground state of harmonic oscillator. That is the smallest uncertainty possible for the ground state of hydrogen atom. Now, as far as the range of nuclear force is because of we know very well nuclear force is because of the exchange of mesons. All right, exchange of meson. So the mass of the meson that is being exchanged in nuclear force is pi meson. And pi meson is roughly of the order of the mass of that particular thing is 250 ME. So therefore, in terms of the mass, so the on basis of Yukawa predicted mass is corresponding as far as that is concerned, mass of the particle corresponds to H, delta P corresponds to H upon R0, which corresponds to MC, that is relativistic particle. So the mass of the particle must be H divided by R0C. Now R0 corresponds to nuclear radius. that corresponds to this, and this is the velocity of light. So you can immediately see then the mass of the object that must exchange corresponds to 250 mass of electron. That is what Yukawa predicted and was found also. Now, it surprisingly, beta decay is almost zero range interaction. Beta decay must be extremely therefore for beta decay the particle must be extremely heavy, and because range is R0 is very small, so the mass will be very large. And as far as the beta decay is concerned, it is basically corresponds to very large energy. Now, in superconductivity, there is coherence length. For a superconductor, Fermi energy corresponds to EF, and therefore you can immediately see Fermi velocity multiplied by delta P. So therefore delta P corresponds to, this is KT, temperature corresponds to transition temperature or superconductivity transition temperature. And that basically tells me that coherence length in superconductor is of the order of 10 to the power minus 4 centimeter. Now, why does the quantum mechanics does not, or uncertainty principle cannot be used in ordinary particles or ordinary mechanical things? Now you can estimate. For dust particle, the diameter is of the order of 1 micron. Mass is of the order of 10 to the power minus 15 kilogram. And therefore, if you use the de Broglie wavelength corresponds to 6.6 into 10 to the minus 6 angstrom, which is much, much smaller. And therefore, you can immediately see that the energy uncertainty is also very small. And therefore, uncertainty products have practically no effect on microscopic dust particle. Now, same thing occurs for coronavirus. Coronavirus also is very small. And therefore, you can immediately see that whenever we have particles which are larger, the uncertainty principle has no restriction, is very negligible. Now, as far as uncertainty principle is concerned, it changed the entire structure of philosophy. Because earlier, philosophy basically says was determinacy. Everything is determined. Laplace wrote a book on celestial mechanics. Laplace was a mathematician, you know Laplace. As far as that is, so Laplace wrote a book on celestial mechanics, and then he presented that book to Napoleon. Napoleon, that was the emperor of France at that particular time. And when Napoleon was given that book, Napoleon went through that book and then asked Laplace that there is no mention of God in your book. Now that basically means the Laplace says that I do not need that hypothesis. Laplacian dream is that nothing would be uncertain, and like the future, the past would be present to its life. So everything is determined, everything can be understood. But as far as the uncertainty principle comes in, you know very well that you cannot determine the present. If you know the present, then you can predict the future. But if you do not know the present perfectly, you cannot predict the future also. In addition to that, Einstein added the principle of locality. With introduction of uncertainty principle, total determinism is lost, of Laplace is gone, and locality is also gone. Because locality is gone because you know very well that whenever there is a photon is emitted from the nucleus, where is the photon? You don't know where the photon is. It goes everywhere. But whenever it's detected at one particular point, it is normally automatically vanished from the other. So non-locality is basically important in locality occurs because of the quantum mechanics, because of the uncertainty principle. Now, resonance particles, lifetime of resonance particles. Now, another important thing that whenever you want to transfer information, you do not want that storage of information should be for example, DNA molecule transfers information in our body. All right. If the information storage, information transfer requires stability, and that stability is so unless the transfer is stable, you cannot transfer information properly. And that is why the molecule must be very heavy so that uncertainty principle does not produce any effect on that. Then Hawking radiation. Hawking radiation basically comes whenever you have a black hole. Near a black hole, because of vacuum polarization, particles and electrons are created instantaneously. That is basically around that particular black hole. But some of the particles enter the black hole while some escape, and that is basically the origin of Hawking radiation. And recently I realized that the arrow of time, because you know very well, arrow of time, in thermodynamics, entropy always keeps on increasing. There was a statement made, or that supposing you have a gas that is filled in a chamber with a shutter, and there is a demon here, and you want to cool. So second law of thermodynamics basically is you cannot cool the object by itself or by transferring energy in itself. So this is basically what says that demon opens the door so that fast moving molecules come on this side and slow moving molecules on the other side. That is basically what Maxwell's demon is supposed to have done. So therefore, if the Maxwell's demon can do that, then in that case, that would violate the second law of thermodynamics. That is, entropy can increase. All right. But you know very well that quantum mechanics says that whenever, now how does the demon know that a particle is moving with large velocity or small velocity? Maxwell has to measure the velocity, and as soon as the velocity is measured, the velocity changes and energy is to be transferred, and therefore you know very well that uncertainty principle will not allow that kind of a thing. So uncertainty principle basically gives you the arrow of time, because all other processes in physics are time reversible, but it is only the thermodynamics or basically is irreversible. Arrow of time basically says entropy keeps on increasing, and it is uncertainty principle which does not allow that process to occur. That is basically what I would wanted to say. And the next one basically says, thank you, I have taken your time. I hope I have done properly.
Thank you, Potware sir. Punit bhai, now the session is open for discussion.
Sir, there is no questions on a YouTube channel or the chat box. So right now, open discussions is carry on. So there is no questions from participants. So open discussion is
just for a minute. Just for a minute, please.
Okay.
Yes,
okay.
sir.
Yeah. Okay. I think Potware sir, I really enjoyed, though in between there was a problem with the link, but it was a wonderful talk. The way you really related uncertainty principle to various phenomena, that was phenomenal. That is what I can say. It was just great. Wonderful talk, and thank you very much. I think you gave a very interesting perspective about uncertainty principle to us. I'm so grateful to you. Thank you.
Yeah, okay.
Though it looks very simple relationship, but how it really is helpful in understanding the physical phenomena, that was great. And you supported it by even numbers. That was just wonderful. Thank you.
Okay.
I made a similar comment in the chat box just now, because the number of examples you gave is absolutely awesome.
Yes.
Very nice coverage of applications of the uncertainty principle across so many different applications. It's incredible. It's an excellent talk, I would say. Really enjoyed it and learned so much from it. Thank you very much, Professor Potware.
Yeah. Can you stop the sharing of screen?
Yeah, okay. Sharing of screen should be stopped at your end. Let me check if I can do it from here. Okay, I'll stop. I think it has stopped.
Yeah.
So, Potware sir, excellent once again. It was pleasure listening to you.
Very nice talk.
Yeah, I am a classical teacher, so this kind of online talk I am not familiar with. So therefore,
But it's really very good.
No, it was superb. It was a very nice talk. I really enjoyed it and learned so much because your coverage is astonishing. The kind of examples you dealt with.
Thank you.
It is very rare to come across such an encyclopedic kind of a presentation,
Absolutely.
where in
Yes.
one go you bring so many dimensions of the topic itself.
Yeah.
Great.
Yeah, if there is no other questions or query, then we can move to the second. Pratul?
Yes, sir. Yeah, I think.
Is there
Viresh,
any?
are you there?
Yes, I'm
Yeah,
there.
you can propose a vote of thanks.
Okay, so thank you, Potbara sir, for really illuminating lecture, particularly started with milestones of science, followed by milestones of physics, and then numerous examples in which applications of uncertainty principles are there, and rightly said by the Asmukh sir and Ahluwalia sir. And particularly the one which I found most fascinating was the tunneling, barrier penetration. It can be explained with the help of uncertainty principle. That is, I think, resounding. Excellent, sir. Thank you. Thank you very much for an excellent talk, Potbara sir. Once again, you remind us the days where when you were to our institute for 3 days and we had a very nice interaction on quantum mechanics. Thank you very much, sir. Thank you.
Okay, thank you.
Now it's time for second session.
Vinod Kumar sir, you can now moderate the panel
So
discussion.
we have
invite
all the panelists around join. We have all the panelists around
Yeah.
in this. Yeah, Professor R.V. Bhatia I have not seen in the list.
No, he has joined.
He has joined. So let us welcome all the panelists. I name Professor R.V. Bhatia, Professor P.C. Deshmukh sir, then Professor Ahluwalia sir, and Professor Joshipura. Kamalan Joshipura, K.N. Joshipura sir. These are the four persons in our panel discussions. We had a very wonderful sessions of around 5 lectures on the quantum mechanics, evolution of quantum mechanics, and till today related to the quantum technologies. And we are actually celebrating this 100 years of many of such important contributions from the great scientists of 20th century. So this is a time where we must think about and see what are the further challenges for the young minds who are coming up. For this, the panelists, I invite all of them. First of all, let me invite Professor R.V. Bhatia. He's a new face for this. He is not a participant of the speaker list. So I would like to invite Professor R.V. Bhatia. He is a very well-known what is called magnetic fluid specialist in India. He is around.
Yes.
Can he shown his face?
Yes, it's on the screen.
Yeah,
Upadhyay sir, namaskar.
Please put your video on.
Namaskar, video is on.
Yeah, okay, now it is visible. So I am introducing you because you are you are not been introduced so far. All other panelists were all introduced. So
I know all the people on the panel or others are there. Because we have learned from them a lot in quantum mechanics as well as theoretical physics.
It's a very well-known physicist, particularly for magnetic fluids and rheology, expert in India and abroad. And he is currently as a provost at Charusat University twice. This is his second term in continuing. And he is not only a scientist, but also a very good administrator. And he is involved in many other committees of various technical expert committees of the state as well as within India. With this small introduction, I welcome you, sir, for this panel discussions.
Thank you
The
very
next
much.
in this is Professor P.C. Deshmukh, sir. Can his video can be put on?
Yes, he's on.
Yeah, Professor Joshibira, sir. So
I'm
Professor
here.
Joshibira, sir, is there as the panelist. So he is also a very well-known figure in this region, not only within the IAPT circle. So most of the activities of Professor Joshibira and his contribution as a teacher and as an educator, a promoter of a young physicist throughout the country, is well known. He is basically professionally an atomic physicist, atomic and molecular physics. His contributions in that region is also very, very well known. Now the next, I invite Professor P.C. Deshmukh to keep his video on.
It is
P.C.
on.
Deshmukh,
Yeah,
welcome
Vinod
back,
Kumar.
sir.
Yeah, I think
Yeah,
my camera is on.
Yeah, we have another very well-known educationist, expert in quantum mechanics and as well as quantum technology. He has been working and giving many talks throughout the country. He has many YouTube channel talks available, many textbooks he has written. He is currently, after his retirement from professor at IIT Madras, he is working in Tirupati as well as many other institutes, which has already mentioned in his introduction earlier. So I don't take to repeat all those things to reduce my time. Welcome you, sir, for this panel discussion.
Thank you.
Next person is Professor Ahluwalia, our president of IEPT. Sir, please keep your video
his
on.
video is on.
Yeah, whereas his face is not seen.
Yes, it is there.
It is there. I'm not able to see him.
Yeah,
Hello,
it
sir.
is there.
Hello, sir. Welcome you for this panel discussion. He is also a very
Thank you very much.
well-known. He is also a very well-known personality from IEPT. Last 3 years plus, he is working and striving very hard to make IEPT a very strong organization who is serving the purpose meaningfully to reach the physics teachers and physics students. And he is also very a good speaker and a very thinker in terms of how certain things can be done. More than that, he is also a very good artist. His paints and all those things. Yesterday in his we could see.
Doodles.
So welcome you, sir. So in this panel, we have expert from, like P.C. Deshmukh, sir, then Professor R.V. Upadhyay, sir, then we have Professor Ahluwalia, sir, and Professor Joshibira. So we have 4, all in different varieties. They have their own stay in physics, their own way they can interact. So with this, I invite all the 4 to be in the panel. I will give more or less 5 minutes for each topic. And I invite particularly one of the panelists for each such topics, but others can also give short comments so that our time can be managed properly. So for the first point here in our panel discussion is the declaration of 2025 as an International Year of Quantum Science and Technology by the UNO is truly a recognition of all the effort and the great works done by the early 20th century physicists of the world. And also, it is also a pointer towards the forthcoming technology, the technological advancement. And then that probably is having a potential to lead to a industrial-like revolution. The next industrial revolution is expected out of such technology. So I would like to have comments on this, the forthcoming technological advancement leading to a possible industrial revolution. First, I will invite Professor P.C. Deshmukh, sir, to make his comment on this or give some of his expertise say on this topic. Professor Deshmukh, sir.
Yeah, thank you very much, Vinod Kumar. It is a great honor to be here amongst very learned people, and you have posed a very difficult question. Indeed, in the last 100 years, we have seen so many revolutionary developments which have changed our life. Means not only, over 100 years, but because of these advances, the way our life changes every 5 years is unimaginable. Even 5 years ago, I would not have imagined that we are using the kind of technology as we are using to communicate with each other. It affects our lifestyle, our communication, even within the families, how we interact with our children, and everything has changed. Grandchildren, I would say. And I talk to my granddaughter, and she uses a vocabulary which is something which I would not have imagined coming from an 8 or 9-year-old child. So the world is changing very rapidly, and I think it's going to be very difficult to predict the way it is going. But I would imagine that some very big advances are expected in biological sciences, in life sciences. And quantum physics, which we are aware governs the laws of nature, but how it impacts biological processes, I think we are only beginning to understand. I mean, there are many things that we do understand in life sciences, photochemistry, and so on. So there are a large number of things that we do understand. But I think processes such as what is responsible for aging, the neural activity, there are a large number of questions which we still don't fully understand. And I suspect that there will be very important revolutionary contributions in the coming decades. And I don't think that we will have to wait for 100 years for this. I suspect that these discoveries are just around the corner, and maybe as early as maybe 10 or 20 years, we might begin to understand many of these things. Now, what this means is that if you look at our audience over here at this meeting, there will be a lot of young people, and they are going to be contributing to some of these advances, and they will be coping up with advances made by others which are unimaginable. So I will like to reach out to these young people and share our expectation from them that they will be up with all these advances, perhaps even push the frontiers themselves. And they have a role which they cannot escape from. Means we find ourselves in the middle of certain revolutions which we had not imagined. And what the young people are going to see is going to be awesome. So I think it is very important that they are on their toes and get into futuristic studies in a very big way.
Okay, sir. Okay, Deshmukh sir. So I would invite now Professor Ahluwalia sir for his brief comment on this.
Oh, thank you very much. It's great to have a panel discussion because it brings diverse views. I am very sure about one thing, and that is that what is going to come in future will have many surprises for us. And those surprises will be led by quantum mechanics itself. And the time has come that in academia, we start realizing these things and think of preparing our students also for this kind of change which is going to occur. I fully agree with Professor Deshmukh that it is not one, say, aspect which will be impacted, but it is going to impact almost everything around us in the society. Something which is coming in front of us is just the tip of the iceberg, and things are moving at an exponential rate.
Yeah.
The way artificial intelligence is impacting, I think it is also going to impact the way we are going to do physics. And
yeah, that is the second point. Ahluwalia sir, that is the second point I would like to have your attention. That is what critical impact will the second quantum revolution, so-called, the second quantum revolution with the ubiquitous application of quantum technology tools bring to bear on fundamental physics and physics education in general?
Yes, sir. Definitely, it is going to bear upon fundamental physics in many ways. Particularly, the way we are trying to understand how our brain works. I think it is going to really make us understand those hidden aspects of our thinking process via the new ways of looking at it, physics-wise also. And physics education is also going to really change as a result of this. We have been talking about earlier that we have three ways of doing physics. One is experimental, then theoretical, then computational. I think now maybe we will focus on saying quantum mechanical way of doing the things.
Plus all together, we cannot isolate yourself.
Yes. I mean, that will be the leader, and that is where physics education needs to really modulate itself to face those challenges in the future.
Yeah.
So
now
this is what I would like to say.
Yeah, I think you may stay a few more, around 10-15 minutes more in this discussion.
I will be actually traveling or something, but I will be listening definitely. And in case I will feel like talking,
some more points
I will stop myself and definitely express my views.
Okay, definitely I will be in touch with you during this discussion. Now, I invite Professor Upadhyay sir to say a few comment related to this topic. Upadhyay sir.
Am I audible?
Yes.
Okay. First of all, thank you, sir, for allowing me to participate in the panel discussion. And I thank IIPT RC-07 organizer all that all 3 days I came out from my administrative job and learned the physics more other than what I am doing in administrative one. So I was very happy with all the lectures I have attended. I was kept myself off from the video, but I attended all the lectures. And I appreciate the Ajay Ghatak's, Professor Deshmukh lectures, Ajay Ghatak's and Ahluwalia's lectures. And Joshi Prasad lecture and Potbare lectures I have heard a lot of time, and I respect Potbare sir because of his way he puts up the things on the very nice plated way that people have to digest as it is rather than going asking any question to him. So thank you very much for RC-07 whole organizer for being a part, and I feel proud being a member of RC-07 first of all. and as an IPT member for such a long. Now, coming back to both the experts' opinion about how the quantum technology is going to make the change, my only concern is the whole panel who are members of the panel, except Pruthul, if I excuse me, we are all above 60, right? More than that, above, greater than that. I don't want to put uncertainty in principle into that. Anyway, it is above greater than 60. But a question here is, who will train our young kids on this aspect? Because if I want to take the 35-year student or 25-year student when he entered in the undergraduate or a postgraduate, if I have to train him for this, where are the mentors for this? One of the things I found very nicely from the that is a IBM side, if you go to the IBM side, they have developed the QSKIT, QISKIT, which is used for quantum computing, quantum codes, and they have given the whole lessons on that. And where they have given one of the whole video, if you look at YouTube, there is that it is non-physicist people also can write a quantum code. Now, these questions puts me into trouble. Why we should teach them into that? If it is a non-physicist can also understand this, then what is the difference we are creating and what level we want to create? So because I appreciate that we should incorporate in our, that rightly said by Professor Ahluwalia that physics education has to change. Similarly, I say the quantum mechanics treatment has to change when you have to treat at undergraduate level or a postgraduate level. Pruthul has put up a few points saying that why can't we train right from the school level teaching kind of a thing. Question here is, can we develop a simulation model without telling them this is a quantum mechanics? Can they understand the science of it? Because this generation, when I say this generation people, they don't like to be inside the class. They want to play with the PCs. They want to play with any simulation chart, and they want to understand what is happening in the real-time world. And that's why we have to develop such a which should be interactive kind of a thing rather than a descriptive way of it. So it's a duty of, I say, all theoretical physicists who are in expertise in quantum mechanics kind of a thing. We have to join hands with the computer people who are AI based or who are the simulation based to develop this kind of simulation packages. Because what is available in the market is a different thing. So what you have to teach them in the school level to integrate is a different thing. And this is the test. What I say that all the experts on this panel, because I'm an experimental physicist, I always feel that I was deprived of learning quantum mechanics and classical mechanics in depth. Because that time, whoever taught us, right, that whatever the knowledge they have given us the knowledge. We are not we are not lucky enough to have Professor Deshmukh, Professor Ahluwalia, or like the people who has put up the whole things, Ajay Ghatak sir and other thing. We have read their books a lot and we understood what we can. But today I felt that after going to brainstorm of 3 days, I feel that I should go back. And honestly telling, after Ajay Ghatak's first lectures, I already ordered for that dancing of photon. I want to understand what exactly that word means and how it works. So this is something which we have to tell our young kids why it should be fascinating. Second point of is how it is technically good and how it is sellable in the market. These people are. Today's question is, are they employable after doing this? So I found out from the last that between 2020 and 2030, there is a 22% growth in quantum technologies appointment in the worldwide.
Right.
Which is the highest I have ever found in any other branch. If you go, it is not a growth of 22% taking place. So these are the certain things which has to be put on their plate to understand that why this subject is important. The last question I would like to ask all the panelists who are there, what they want to learn, quantum mechanics or quantum physics you have to teach them, or quantum science you want to teach them. So these three terms has to be well defined when we start teaching in undergraduate level. Thank you very much, Professor.
Yeah, definitely. Definitely, your points are very important. It is I rightly said that the employment opportunities are growing in this field in different ways. Unexpectedly huge fashion. So we cannot keep our youngsters away from that stream. So that is why the panel discussion is important. How we can go ahead. It is not meant for the 60 years plus. It is for the youngsters starting from the school level. Can we give, in what way we can associate them in this, the whole quantum science and quantum revolution I am talking about, quantum technology I am talking about. It is not on just theory, not just on understanding quantum physics. It involves a lot of high sensitive device making, material science, the quantum dots and other things which are all minor scale and long scale reduction on devices and so on. So it involves a lot many physics or the technological aspect. So that our youngsters from India cannot be far behind it. Many countries are moving ahead with their own missions. Now, with this, I invite Professor Professor Joshibra sir for the next topic, that is from Indian context. Joshibra sir is around?
Yes.
He's hearing.
Yes.
From Indian context, how can we equip our young generation, particularly students, to cope up with the new technological order in terms of preparing them for the human resources needed? I'm specifying the word human resources, the future human resources needed to support and develop our own quantum revolution technology.
Very
How we
nice.
can-
First of all, yes. Can you hear me?
Yes.
Can you hear me?
Yes, yes,
Yeah.
yes.
Okay.
Yes, sir.
Thank you so much. We thank Professor Aluwalia for this 3-day event. For me, it was an occasion to learn, unlearn, and relearn. And I feel myself to be a student at this age. Very nice of you. And the point that is raised by Professor Vinod Kumar may be little different from what I wish to express. But in any case, please allow me to express a concern, and then by IAPT can carry out activities. For example, training teachers, first of all, teacher awareness, which will percolate into students. My concern, the universe of knowledge is expanding. It is accelerating, expanding at an accelerated rate. This is one thing. And therefore, even with the present knowledge, you have a very large band gap or increasing band gap, because the knowledge is increasing, and we have to cope up with the increasing knowledge. This is one kind of a challenge, The other kind of a challenge with which I'm concerned for over 2 years now is that the present level of physics education, present level of physics contents has gone down. This is challenge or concern number 2. We should be from here to here, but at the present rate, we have gone from here to here. So that adds to the challenge, that adds to the concern. On one hand, we have to regain the level which is required to understand quantum mechanics, quantum principles, which will lead to technologies and applications. And on the other hand, we have to maintain the level. So this is a twofold challenge, which I've been telling very frequently. You will please excuse me if I leave a little earlier, but this is my challenge. Okay, now, so what do? We have been organizing, IAPT RC-07, we have been organizing online programs where there will be students, teachers, school teachers, some of them are enthusiastic. And now we will include common men, engineers also, and let us see their response, how they feel about it, how they feel about the new changes. So change is a challenge, and in the present case, the challenge is twofold. Knowledge level required going up, knowledge current level has gone down. Thank you so much. Thank you.
Okay, the idea is that we need to prepare our future human resources who may be able to handle the technology which is coming up. We cannot keep the technology. I shut on the technological advancement, particularly in the quantum technologies which are in the market, which is developing, which is in the moving very fast. So whatever be the issues and problems associated with the present day scenario of education, particularly in physics, but we need to see how it can be overcome, how we can make our own next generation equipped for this. We make them ready for accepting such, not just as a user, as a developer.
Yes.
I don't mean that, Professor R.V. Upadhyay sir has said that there are many things developed at the IBM and many other private companies. They allow us to use, but what we want is, create new technology, be part of the creation within India.
May I say very briefly? What we have been doing here in Gujarat is to connect teachers from schools, teachers from engineering colleges, teachers from science colleges, may not be very, very big in number, only a small group. I propose with now Professor Vinod Kumar and Pruthul Bhai, a small continuous working group, very informally, quietly working to see how the band gaps, as I mentioned, could be reduced. It will be possible. I have started talking to people and they have shown interest. And there are at least 10, 12 people who will work with this. It will be a continuous working group, not just online talks, continuous working group. They will prepare items. They will also have some sort of videos or online lectures or even written material. It's going to be a long program, not just like 1 hour online program. This is my proposal. I'm
It is
working
nice.
on it. I've
Professor
started.
Alivali sir is around now. Professor Alivali sir is around. Hello.
Seems he's not there, sir.
He is not there. So probably now the next topic along with this, I invite Professor P.C. Deshmukh once again to address this issue. As quantum technology such as improved, Professor Deshmukh sir is hearing, right?
Yes, yes, yes.
Yeah, the quantum technology development, particularly the quantum correction, improved error correcting quantum codes. That means fault tolerant quantum computing, entangled quantum sensors, quantum teleportation, etc., is in the advanced stage of study. What doors of basic science can these tools unlock?
Yeah.
It is a give and take, no? Many
Yes.
times, many advancement in technology will also lead to understanding more basic of nature. Basic
Absolutely.
properties associated with nature, which was not so far unveiled.
Absolutely. Very good point, Vinod Kumar. Before I get into it, I would like to make a small comment, which is not related to your question, but related to the opportunity for me to be a part of this discussion. Because when I'm with RC-07, I feel so much at home. Because all of you means, of course, with Vinod Kumar, Zoshipura, Pruthul, I have been interacting for a long time, but also with Professor Upadhyay, who I had a meeting last year. So I feel very close to RC-07 and I feel very much at home when I'm with this group. So thank you very much for that. Now, coming back to this point, you're absolutely right. Means with quantum entanglement, there is an opportunity to do problems which we could not have attempted earlier. There is no question about it. But the biggest challenge in using quantum computing is indeed that of error correction, because qubits are very fragile. And once you entangle qubits, these qubits, at the end of the day, these are physical objects. These are physical objects, and no matter in how much pure and clean environment you house them, they can sort of collapse due to any impurity, even the slightest of impurity that may be there inside the apparatus. And that is where fault tolerance has become an important challenge. And I believe, means, of course, I'm not completely conversant with this technology, but what I hear from some people who are working in this field, I see that the biggest challenge is not so much in how to achieve quantum entanglement, but how to sustain it against possible impurities and how to handle error correction. So many advances have been made, I think, in the last 5-10 years. And these advances are necessary because there are fundamental challenges to humanity. Means we have just come out of the COVID era. And those 2-3 years, almost everybody we know has lost somebody close to him or her. All of us have lost somebody in the family or somebody amongst our close friends. I think especially people with comorbidities and so on have been only fortunate to escape. So there are these challenges, and this requires, inventing new drugs. And quantum computing will go a long way to solve this problem. Now, this is where the error correction will be of great importance. And I'm expecting some major advances in this in the coming 5 to 10 years.
Definitely, even at the realm of quantum sensors is moving very fast.
Yes.
Because that is also equally important to read out.
Absolutely.
Whatever is the result coming out of quantum computing.
Very
so
true.
the quantum sensors is also going in the molecular level.
Yes.
So that also may lead to many things. I recently read somewhere that we are able to detect the gravitational force between two atoms at some in a molecular system, and how that gravity may modify even the electromagnetic coupling strength. So these are some of the issues that people are now discussing. If we could reach to that level of precision in measurement.
Vinod Kumar,
May I
Professor
come in?
Ahluwalia has joined, so
Yes,
let
definitely.
us hear him.
So thank you very much. I was listening everything, but because I was driving, I have just come on the side. I just
no problem.
really
You're welcome.
want to really comment on few things which were shared by the fellow panelists. One is this that, and I would like to emphasize it, IEPT has to play a big role in it, not a small role. I think we have to think big.
Yeah.
I have been, talking to very many people, even at the highest echelons of thinking process, even at Niti Aayog kind of a thing. And, they are worried about one thing, that even today in our universities and even in engineering institutions, we lack that kind of a thrust for courses which are needed to bring this kind of a change.
Yeah,
And
Ahluwalia
we
said
need
that is the minute. That is actually the point, the next which I am putting forward to you. And Professor Joshibara and Arabi Vadya sir to comment. Can we prepare an effective curricular framework at all levels of education, say starting from high schools, and how do we go ahead? I hope you are addressing that one.
Yes.
Yeah.
That
So
is
that
what
is why I
want.
thought you to say specifically mention this point.
Actually, that is where I would like to really even work for this year in the of IYQ.
Yeah.
And we have all the possibilities to work in that direction in a very, very structured manner.
Yeah.
What we can do is we can really make a group, which we can call as the uh, uh, what you call courses group or syllabus group or whatever you name you want to give it, and look at it very carefully, keeping in mind what is happening in the formation of this kind of a syllabus at the national level. Because I think we must really synchronize with that. And IEPT should bring out its own model for doing it. Because, we are not just worried about how the things are happening at the national level, but IEPT should bring a model for which people should take notice. I think that is the effort which we need to really make. And for that, we need to really, I think IAPT now, ever since, we have been able to meet together on Google Meets or Zoom or anywhere, possibilities are immense. And I would
Yeah.
appeal to the
Mm.
members who are in this particular discussion that let us really think and not what
Definitely.
happened. And I think I
Definitely.
will start with
Yeah.
something which is there in my mind. I will
Yeah.
create a Google Classroom to work in that direction. That I can assure you.
Yeah.
Thank you very much.
Definitely, it is going to synergize the low students opting physics, low level of. I mean, the number of students who are now opting for physics is going down. Probably this way of attracting them towards, showing them towards the new development, technological development which is forthcoming, probably will attract them back to physics again. For this, I would invite Professor R.V. Upadhyay's comment. Can we really go ahead in particularly framing some curriculum at the level which we can, maybe high school level or maybe at the undergraduate level, and then bring them to train them towards this?
Yeah, one of
Professor
the things I
Upadhyay.
will always appreciate, one thing is I respect Professor Ahluwalia's suggestion, what he has done the task force. Now, problem here in every our institution or any university comes is, if you start introducing it at the school level, right, the question will come, so many questions will come. But if you look at the undergraduate level introduction, because you require three things very clearly in quantum computing and quantum programming, they should be good in linear algebra. And as rightly told by even Joseph Sahib was telling, the mathematics has been removed from the courses now. All right. So they are only looking at the engineers have removed mathematics from the whole part sometime. So programming language, that is quantum programming, has to be a part of the syllabus somewhere first. Just like you have C programming, this programming, like that, you should have quantum programming. So aiming a syllabus, doing it entirely, giving the whole homework is a one part. But who will deliver this? Who will make the transformation of the syllabus to the teaching? We have to focus on this, that we have to create a people who can do real translation of your syllabus to the students. And how best they can do, that is going to impart on also how best we can get the student.
Yeah.
So our focus under the syllabus, go to the teachers first, who are interested, who has got inclination to learn this, identify them and make them how they can teach this subject and what level depth of. Because Feynman lecture series 3 gives you a quantum mechanics anyway, full part. Everybody knows Feynman lecture series, but how to learn is the impact. Definitely. So the IIPT RC-07 or all the entire IIPT should focus on that how we can transfer this knowledge to the teacher first. Definitely. Then you decide what kind of, because programming is a language, has to be written by something, right? So we have to isolate and then introduce either at UG or PG level rather than going to the school level expert. This is my suggestion.
That is good. Do you think that this way of modifying or invoking teachers training maybe at the first level and identifying experts within the country to teach them or take some of those lessons, and then slowly there is a possibility for our physics education shifting their focus towards the new forthcoming technological advancement?
Yeah, because see, if you look at it, AI thing has come now. Artificial intelligence, machine learning has developed. So people have started weaving on that. But those who have got a computer programming knowledge, it is not necessary now. Even they can use as a tool.
Yeah, that is the point.
Like quantum tools can be used for studying so many things. They don't have to learn programming or anything. But application of this tool to their study is more important to make them aware of it. That's what my point.
And such a program should not barricade all the engineers and others, mathematicians. Everybody can join in such a scheme. It is not physics alone or engineers alone. That separation should not be. Yeah, they all require, particularly mathematician, physicist, maybe a computer specialist, all these three together. So may sit together and then plan out for such things.
The things what is happening in recent cases is old people get scared when they learn quantum mechanics as a subject. Students get scared of it. Oh, it's so much mathematics. How we make them enjoyable while learning is an art.
That is
so
maybe
why I appreciate the people also are panelists, the way they have presented, that makes us feel happy that it has been different way people has to teach. And this training has to be given, irrespective of whichever the course you want to introduce in physics.
This should be planned for teachers. Yeah. Mainly students are not attracted because of the way it is being taught. You are correct in that sense.
Absolutely.
That is why Professor Alubali sir is also focusing on physics teachers. I mean, not only physics teachers, mathematics teacher, as well as computer training. So the computer specialist should be taught the basics of these things. I mean, teachers first, and then together should be evolved.
Have a
Not
small
just
group people start
yeah,
with,
small
suppose
group
RC-07 can take initiative, a small group of 5 to 6 who can be trained in this particular, how to teach the subject of Penman lecture series, how to make them attractive to students to learn first.
I think
then we can do the rest.
Definitely we can look forward to Alubali sir's suggestions, making a sort of a group, working group, work about it, and then slowly plan out program for teachers particularly, and then look forward, not taking a long time where everything is developed and then we will be at the receiving end alone. Not at that stage. Probably we should start at the initial stage itself, after few training courses and identifying few teachers who can put justice to this field, and then it is right time. At that time we should plan for some courses, special courses also. It can be involved other than the regular other courses.
So that is why I appreciate Babulal Saraf's methodology of making them people to understand what the scientific tempo is. He went to pole to post on the vehicles, right, and make them understand what is quantum mechanics by the experimental proving in that. So this kind of initiative has to be taken for if you want to really make them love for the subject. I was lucky enough to have traveled with him entire Gujarat when he was visited Gujarat during that time. I was in his car, whole Karwa. I was along with him throughout all the places. And that made me very happy that it is nice. That way that we have to do this also.
So in India also, because of the quantum mission, etc., there are a lot of efforts going on. Probably in Gujarat, we have not seen so much of enthusiasm in this, but in various other universities, people are really working and putting forward the educational aspect of this technological, various aspects of this technology. And I think, Pratul, we have still time. Pratul has few more points here, how we can introduce quantum concepts in the education, how advancing quantum education at the college level, and then public awareness and outreach, quantum technology linking, how it is the practice and the theory can bring together. These are the various points that we need to discuss. I think Professor Joshi sir is also missing, or he has gone?
Yes, left, right. He is not there. Sir, I just wanted to, if you, with your permission, I would like to add.
Yeah, definitely. Please go ahead.
Sir, what I understand, see, these quantum technologies are essentially based on, idea of Bell inequality and, entanglement.
Definitely.
Now, in a typical quantum mechanics course in any of our universities, at least most of our universities, because see, when we studied, this was more of a question on foundations of quantum mechanics. So that part we never studied, entanglement or Bell's inequality when we were, taught quantum mechanics. Even today in our curricula, we still have not been able to include these topics in the regular discourse. So not even at PG level. So now when the teacher who completes PG and then becomes, say, maybe he clears NET or something, and then he becomes a lecturer or maybe a school teacher. The problem I feel is that he has not undergone the training, or rather he has not, been taught or learned this subject to the level that he should have. I think so. That's why, we need to change our curricula. And once again, who is going to teach that is, I think, the most.
That's the first point. So we require, IAPT is looking forward probably to train, group of teachers who will be, ready to deliver, or maybe ready to get trained first and then deliver to their respective levels of teaching.
So I am, sir, requesting both the experts, Deshmukh sir and Upadhyay sir, how do you introduce, say, a topic like quantum entanglement and Bell's inequality, and then, of course, these experiments Clauser's experiment or maybe Aspa's experiment, how will you integrate it in a regular curricula at maybe say PG level, because already students find it difficult to learn non-relativistic quantum mechanics, then relativistic quantum mechanics, and then you'll have to add these very crucial topics too. But we'll have to do that. So I am really eagerly looking forward to the comments of both the panelists, how they feel we should be going about introducing these topics even at UG, if not UG, at least at PG level.
Pruthul, I think that these topics can certainly be taught for our MSc students without any difficulty. I think part of the difficulty is the fear of mathematics that students have. And I must say that we are responsible for that fear. We should alleviate that fear. We keep telling them that, okay, this is mathematical, this is difficult to understand. I think we have to stop saying it. Because let us remember that in our country, in Bharat, we have a rich heritage of mathematics. We invented the zero, the number system, and so many advances in mathematics have been made right here in India. And we should tell the students that, okay, they have this heritage, they have the capacity to learn, and we should encourage them to learn. Actually, the mathematics which is involved is not at all difficult, because when the students come to MSc class, they have already finished courses in mathematics in which they have studied. They are introduced to calculus. They know how to solve differential equations. They know how to manipulate matrices, how to get the inverse of a matrix. And if you know matrix algebra and differential equations, you can learn quantum mechanics very thoroughly. You don't have anything beyond it. Now, if we keep saying that, okay, this is difficult, they also start believing that it is difficult. So I think all the teachers have to make a resolution that let me not avoid mathematics. Let me not go to, for some shortcuts, give some hand-waving arguments, give them rigorous solutions. Because the mathematics which is involved is very straightforward. There is elementary vector algebra, vector calculus, differential equations, matrix algebra, matrix manipulations, and all of these things they study in first year, second year, third year BSc.
Yeah.
Why are we not using it with confidence? If we use it extensively, get them used to it, make them comfortable, make it enjoyable, because I think solving these problems can be made fun.
Right.
And I think we need to embrace mathematics in a very big way. We should stop saying that, okay, let me try to find some easy way of explaining it, avoiding. What are you avoiding? What you are avoiding is a very simple differential equation.
Yeah, definitely.
Which they know how to solve.
Yeah, even to add to your comment, even to understand the the so-called Prithul's concerns about Bell's inequality and EPR paradox, you don't require that much of detailed mathematics.
Absolutely.
Like even like to solve how the WKB approximation solution around the classical turning point. Even that level of difficulty is not there. Once you understood the concepts, philosophical details, the mathematics is not that difficult. I still feel that it can be introduced at the TYBSc level. This two topic which Pratul was talking about, that it has been not been a part of the quantum
And
mechanics.
actually, the topics are there in the syllabus. Teachers know how to solve those problems, but there is a mental block to getting into some of these details. And I think this is where IIPT can play a big role.
Right.
In generating a sense of comfort, a sense of confidence that, okay, we can handle it.
Yeah.
And as a matter of fact, discover our own capacity to deliver. So I believe that the capacity is there. Means when we worry that, okay, how are we going to incorporate this? I think the capacity to deliver is already there. The potential is there. I suspect that it is not being used fully.
Okay. Okay. I now invite our secretary Regaben to say a few words. Regaben is there?
Sir, Rekhaben nahi hai.
Okay, so now I think it is time to come up. Short of time, we are past 5 minutes more. So let us conclude saying that IAPT is expected to do a lot of groundwork in particularly training our physics teachers first, and then introduce and chalk out a curriculum framework which we can introduce at the different levels of education. With this, I thank all the panelists to putting their views and suggesting the way to go ahead for preparing our next generation to cope up the quantum revolution to technologies. With this, I thanks all the give my thanks to all the experts sitting on this panelist and their thing. Back to Pratul.
Thank you, Vinod Kumar sir, for summarizing this, I think, excellent panel discussion. I think we covered almost all aspects of, how to educate teachers, what is the role of students, and, how to go about, and so that we can, keep pace with the rapidly changing, scenario world over, and with quantum technology or quantum revolution round the corner. So I think this concludes our 3 day session, 3 days, 3 day program, wherein we had five excellent lectures from some of the most prominent and experts in the field of quantum physics. And equally, at the same level, we had very nice discussion or panel discussion. So on behalf of IAPT RC-07, I would once again like to thank all the speakers who spared their valuable time and then discussed the ideas at length. And at the same time, I would also like to thank all the panelists who gave us their insightful ideas regarding the future or how to go about with this quantum revolution in terms of putting it in curricula and then bringing up the levels of teachers and so on and so forth. So I find that such discussions really make us focus on a particular aspect of physics. And I think I would like to thank the president of IAPT Ahluwalia sir for giving this excellent opportunity to RC-07 for hosting this curtain raiser. And I'm sure with this successful program, I'm looking forward to, we all are in fact looking forward to many such programs across different RCs across the country. And once again, this churning process of thinking and then coming up with some solution, thinking again. And so this churning process, I think, has been initiated or started. We have started the ball rolling, and I'm sure that we would be able to raise ourselves to the level that is expected when you have such an important revolution, imminent revolution round the corner. So I once again thank you, all the participants who have spared their time, all the dignitaries, the experts, and our own president, Vinod Kumar sir, the entire, EC team of RC-07, and especially Rekha ma'am, the General Secretary of IIPT, who was kind enough to give us this online Zoom online platform. Not only that, she started all the meetings, she was present throughout. So all this thing is quite encouraging for all the RCs and for all of us. And I'm sure we will bring about a revolution of our own in terms of how to teach, how to go about in this quantum revolution. So I think I would like to once again thank all of you, and I'm looking forward to many such discussions, fruitful discussions in future. Thank you once again.
Thank you, sir.
Thank you.
Congratulations to
Thank you,
RC7.
sir.
Congratulations and
Thank
much
you.
gratitude to RC7.
Thank you, Deshmukh sir.
Thank you all.
Thank
and
you,
bye.
Upadhyay sir.
Thank you.
Thank you, Alvalia sir. Thank you, Joshua sir. All
Okay. Bye.
present in the
Okay.
discussion.
So I think our session and program ends now. Thank
Yeah.
you.
Okay.
Okay.
Okay. Bye-bye.
Bye.
Bye. Thank you.
Why not have a last photograph of all the participants?
Oh. So all the participants.
There are 16 only now.
Okay.
It's not possible now. Okay.
Okay.
Yeah.
Thank you.